to our second meeting in Mechanics of Materials. How was the assignment? Straightforward? Okay, good. We're going to try to do something similar for the subsequent questions as well and problems. As long as I have some time, I'm going to attempt to create some videos that will hopefully be helpful to completing the assignments. Don't worry, the questions are going to get significantly harder through the course, okay? So if you're like, oh, I know all this stuff, well, that's good. Today, again, you probably will be pretty familiar with the concepts that we're going to present, but maybe it's a slightly different twist than what you've seen before. Any questions before we talk about some administrative stuff? Questions? Comments? Yes?
Do you upload the slides on Canvas at all?
They will be on the website. So the slides for today are on the engineering-content.com website. Yeah. So they're there. Yes?
On a test, are we going to be provided with like a sheet of units and stuff?
Okay, so good question. The question is, on the exam, what will you be given? Okay, so you see there are example exams as well. We talked about this. That's what you'll be given plus answer sheets. Okay, you will have the opportunity to bring in one sheet of notes. They have to be handwritten. Anything you want on them is fine. Problems, whatever you like. It just needs to be handwritten. Okay, and yes, if you have a tablet and you handwrite on your tablet, you're fine to bring in a printout of those. Okay, but what we don't want to see is copy and pasted stuff. All right, so that's how exam 1 will go. Exam 2, 2 sheets front and back. 8.5 by 11 or A4 size, and then the final exam 3 sheets front and back. Okay. Other questions? All right. So I also uploaded to Canvas, all right, a new syllabus because there's been a slight change in plans. So here is the new syllabus. No, that's not the new syllabus. Where is the new syllabus? Oh, I clicked on the wrong one, sorry. Okay, this is the new syllabus. On Tuesday, we're going to have Alex Ruiz come in and have a safety training with us. Okay, so we're instituting something a little bit different. There is a lab component, and if you get hurt in this lab, I would be very surprised. Please don't. Okay, it's not. I mean, you'd have to like twist the bolt onto your finger or something. Okay, it's very safe. All right. Nonetheless, because there's a lab component, we're going to have REHS, Rutgers Emergency and Health Services, come in and give an official presentation. And if you attend, you will get a certificate that you can take with you through the rest of your time at Rutgers with just an online refresher. How many of you done the REH certification for lab safety? Okay. So I tell you what, it'd be great if you come, but if you are so inclined not to come, take a screenshot of your current certificate, and then put that in as your attendance, okay? For everybody, it has to be current. It has to be current, okay? And so once you have that certification, the first time you have it, it's supposed to be in person, okay? And then every year after that, you can have an online refresher, right? Any questions on that? So if you are not going to be here on Tuesday, all right, then please sign up to take the REHS safety training at one of their sites, okay? We will not begin the lab until after session 6, all right? So we have a lot of time still, okay? Because you kind of need that material to be able to do the labs. That means so please schedule, and and then I'll explain something. So please schedule, if you're not going to be here on Tuesday, or if you miss it on Tuesday, I really do want you to have that certification. And for your labs to be graded, the first question is going to change on the labs where you upload that certification. Okay? Any questions on that? All right. What is going to happen? I talked about this a little bit previously, but what will happen with the labs is we will, I hope by Tuesday, have essentially a very simple Google Sheet where you sign up. Now, we're only going to have 19 sessions of lab. Okay, only 19 sessions. And we can only handle 9 people in each of those sessions. Okay, so do the math. Or can I do the math? That's 9 times 19, right? Or 180 minus 9, so that gives us 171 slots. There are about 148 people right now registered for this course. So we really need everybody as soon as it comes out, well, maybe not as soon as it comes out, but you need to pick a slot, okay? And please don't change it around because that will make it inconvenient for other people. The slots are during this class, right? So as long as you are normally, there should not be any conflict. Like we said last time, you'll still be responsible for the assignments, but you just get to watch the video online. So you want to prepare in advance for doing the lab and having the overlapping format. Okay, any questions on how we're going to administer that? Yes?
What will the spreadsheet open
I should have it by Tuesday, okay? So hopefully over the weekend. After I get the next set of videos for the homework assignment done, I'll get the spreadsheet out for you, okay? All right, just note the dates for these assignments, their due dates, they're changed on the syllabus, but I haven't yet gone into Canvas and changed them, all right? So what will happen is that this assignment, I think we'll still have it due on Tuesday, but these other ones are going to get postponed, okay? Just by one day because of the REHS. We had a buffer actually as session for 12:10, and now that buffer has been taken with material, okay? So it was a lucky thing. I was like, how are we going to fit this extra training in? And then I looked and it's like, oh, okay, we have a safety factor. Okay, so that's where we are on those items. Let's go ahead and start on the technical stuff. And I guess assignment number 1 was pretty straightforward because I didn't get any questions. It's like a first. I don't know what's going on, but I think that will change as we progress. I have office hours after class on Tuesdays and today, and then Praj has office hours on Tuesdays at 5:30, I believe, and on Thursdays, yesterday at 5:30. Okay, so again, we have some time, and we're happy to talk with you. Today is going to be a review on static equilibrium, and it'll be a chance to kind of revisit some of the wonderful things that you got to do last semester, or maybe it was 3 years ago, whenever you took statics, okay? And maybe it'll be a little bit different approach because we very much want to emphasize, well, whether it's the same approach or a different approach, what we really want to emphasize today is being able to understand the internal moment, the internal torque, or the internal force that is within a structure, okay? And last time, we discussed the 3 types of structures that we're interested in studying in this course. We have the bars, we have torsional loading, and we have the transverse loading of a beam, okay? And we did describe the different types of scaling laws for how much load each one of these structures could handle, right? So this is just a one slide kind of recap of what we did last time. And these same structures are what we're going to look at today. And the goal is under conditions for static equilibrium, we're going to be able to say, okay, this is the internal moment. This is the internal force, right? This is how we approach this. This is how we do the method of slices. Okay. So to do this, we go back and we reflect on Newton's laws. All right, so the first law is a body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. Okay, and if we think of the equation that we might write here, P being momentum, right, is equal, and this is a vector, is equal to the mass times a velocity. Okay, so you've seen this before, and this equation will not be one that we refer to a lot, but it's still nonetheless good to remember. This equation related to the second law, when a body is acted upon by force, the time rate of change in its momentum equals the force. This one we will use a lot, okay? But what is P dot going to be equal to?
First derivative?
Okay, well, but, right, they tell you in class, yes?
Mass times acceleration.
Oh, okay, yes, that's true. And in this class, because it's a follow-up to your last class, that P dot will have quantity equal to? Zero, okay? That is, right? And so you can think of this F as kind of the summation of all the forces for a particular system, whether it has an internal slice or if it has a an external equilibrium that we're presenting, okay? So force and the rate of change of momentum. Okay? And the last one, if two bodies exert forces on each other, these forces have the same magnitude but opposite direction. Okay? So I think you're probably pretty familiar with this, right? So like if I have this little cantilever beam here, and I have object 1 and I have object 2, all right? I have an action-reaction pair where they touch each other, right? So there's a force from this object acting on this object, right? And there's an equal and opposite force from this object acting on this object, all right, on the pen, right? So you're familiar with that. Now, let's think about the analogies when considering rotation. Okay? Again, we probably won't use this equation very much in this class, okay? But we can think of angular momentum as being the angular velocity times a moment of inertia. Okay? And that's the first law. And the second law, which we will use a lot, is saying that the summation of the torques or the moments will be equal to I omega dot. All right, so we have a moment of inertia times an angular acceleration, and that angular acceleration we hope will be 0. Okay, so that. Now the third law does not have a true analogy. Okay, and why? Let me just put up an example for why that's the case. Going back to us putting force on this pen, okay? Object 1 and object 2, okay? Now, I know from my physics, right, that a moment or a torque is equal to R cross F, okay? So now, if I apply, let's say this is like just an object in space, okay? I can apply a force here, and I know that I'm going to have a moment, okay, being applied to this object, and there's going to be essentially, well, the moment at this location, right? You have to specify location where my fingers are, right? That's going to be the R cross F, right? So whatever this force is, right, and I'm going to have this thing kind of applying it like this, right, to give it a torque, to give it a moment, right? And there will be a reaction moment from this structure, my fingers, on this pen to balance that out, okay? But there's no moment being applied to this object, okay? It's a force, right? The third law is applicable to there being an equal and opposite reaction, right? Where there's a force being applied to this, my finger object, okay, but there's not going to be a moment applied to this object, okay? So it's not a true analogy, okay? But we're going to see lots of cases where if I have torques or moments being applied in a collinear system, right? So here's an axis through the pen rotation, right? I apply torque this direction, and I apply torque this direction, right? There's going to be kind of what you would consider to be like equal and opposite reaction torques being applied to that system, okay? But the analogy kind of breaks down for two different objects that are not acting, or the torques are not acting in a collinear fashion. Okay, any questions on that? So we've established Newton's laws, and the kind of place to review what you might have caught in studying statics would be in Hibbler's book, okay? Or I guess I threw out an acknowledgement to the book I used when I was a student. We'll have a couple of references to it throughout the semester. I'm not quite sure where you get this book anymore, okay? But anyway, I still have it in my office. So these are some of the resources you could use if you want to review your statics, and these are some of the exact sections from the 14th edition of Hibbler's book, okay, on that. Now, for static equilibrium, we write these equations, right? The sum of the forces is equal to 0, and the sum of the moments is equal to 0, okay? And if we have, the opportunity to write it out in multiple directions, we say the sum of the forces in x is equal to 0, the sum of the forces in y is equal to 0, and the sum of the forces in the z direction is equal to 0. Similarly, we do this for moments. So the sum of the moments is equal to 0 in the x direction, and we should probably specify that this is, we have to select, we must select a location, okay, for this to happen. So in this example down here, right, what we have is our famous cantilever beam. We've made a coordinate system. This is pretty standard, where x is along the axis of the beam, and we have z coming out of the board at us, given by a dot, and we have y, right? And then if we look at external equilibrium, okay, what do we have to have? Well, the wall can provide a reaction moment, and it can provide a reaction force. And so we have this P here, and we have FR over here. So maybe, summing the forces in X and summing them in Z is probably not that interesting here, but we can sum the forces in Y and say they're going to be equal to 0. And so if we say that FR is in the same direction as Y, that's going to be a positive. And then P is in the opposite direction as that's equal to 0. Okay. And if we give this beam some length, okay, we can look at summing the moments about Z, and we'll say at left side. Okay. And that means that, okay, is MR in positive Z or minus Z? Which direction is it? Which way have I defined it?
Positive?
Yeah, positive, right? It's coming out, right hand rule, boom, bang. All right, so we have a positive MR. Okay, now what about P? And what's it doing? What's its moment R? Anyone? Yes?
Negative.
Negative, all right, so what do? I do minus?
PL.
Yeah, minus PL, right? And that's going to be equal to 0, right? So this is how we can figure out, some unknowns. We didn't know what the reaction force was, assuming that we knew the length and we knew the P, right? We didn't know what the reaction force at the wall was, but now we can figure that out. And we didn't really know what the reaction moment at the wall was either, but now if we know P and L, we can figure it out, right? So this is just a straightforward example of equilibrium that you've applied many times in the last semester. Now, what we're going to do today is going into a little bit more depth on the three primary structures of this class. We're going to talk about axial loading and how we think about equilibrium. We'll talk about torsional loading, and we'll think about how we use equilibrium. And we'll think about transverse loading, and again, how we use static equilibrium. We'll also talk about trusses. Now, there won't be a question on trusses in this problem set, but there will be analysis done on trusses in a future example, and so I still advise that you kind of pay attention. Okay, so for equilibrium and for calculating it, there are kind of two big steps. And this is pretty much for all structures, but we're talking about bars now. What's the first thing you do? The first thing you do, well, it's written there, right? It's the first thing you do when you, I don't know, does anyone, free body diagram, and on what? Because I'm going to do like two sets of free body diagrams, foreshadowing, right? I'm going to do free body diagram on what? Yes?
The bar.
Okay, the bar, right? Yes? Right. So you're going to essentially do a free body diagram on the whole system, all right? Whether it's a shaft, whether it's a bar, whether it's a beam. First thing you do is you do this external equilibrium, right? So we're going to draw the bar, like you said, do a free body diagram, and it's just a chance to observe my beautiful drawing. Okay, so and we want to define a coordinate system or axis, and we want to apply Newton's second law, right? So this is just putting the circle on the whole thing because we're doing external equilibrium. Okay. Does anyone have? I'm just thinking what's the first thing you do when you get in the car? Buckle your seatbelt. That's what you do. Does anyone sing that song? Okay. I don't know, but what's the first thing you do when you get a bar? External equilibrium. That's what you do. Okay. Now, we are going to sum the forces. This is using Newton's second law, and it's very boring here, okay? Because this is not accelerating. All right? So that's all happiness. Probably no question on this. So what's the second thing you do? Well, the second thing you do is you take a slice. Because what we want to do is figure out what the internal force is. And now this is a little bit more thought-provoking, okay? To say, I kind of know what equilibrium looks like between two objects, right, using the third law, okay? And now what we're saying is there's actually an internal force that's being supported by this bar, okay? And so the way to do that is take a slice and use method of sections. If any of you like Jeff Hansen, all right, that's great. What does he call this? Anyone know what Jeff Hansen would say here? Come on. I know you were watching Jeff Hansen. Come on. No? Okay. Well, he would say this is the cover-up method. Okay? Where essentially you take your object and you cover it up on one half. Now, does this sound familiar? And you just look at that half of the structure. Okay? So we've essentially taken a slice right through here, okay, and we're covering that whole thing up, and what we get now is this bottom. Okay. And I alluded to this last time, probably not very clearly, but when you have a cut open surface, right, and you've done surgery here, what we typically do is we define a normal vector, all right, so this is a plus z in this direction that's coming out of that surface, okay? And what's interesting is that this surface, depending on how you do the cut, like this, you see now this is covering up the bottom portion, right? So now we've got the top exposed. You see here, we have now a surface with a force coming out, and I would suggest that you often define the normal vector coming out of that sliced surface as being positive. Okay, this is applicable to torques, it's applicable to bars and forces, okay? Now, do you see here, there is an interesting thing that has happened. This, let me get rid of some of this. This plus a z, which is a coordinate system that we said we were going to define when we did external equilibrium, is not in the same direction as this plus z that we defined when we did method of slices. Does this mean that the world has come to an end? No, of course not, right? It just means that when we write out our equations of equilibrium, okay, algebraically, that we need to make sure we know which system or which coordinate system we're using when we do that math. Okay? But I could still, and you will, still combine the external equilibrium equations with the internal equilibrium equations, or from the method of slices, algebraically, but they will have a different, they could potentially have a different coordinate system. Or it could be the same, okay, depending on how you define it. Right. So, are N1 and N2 equals? Well, they are equals in their magnitude, all right? But they seem to be acting in opposite directions, okay? But they describe the same behavior. Okay? So, what is that behavior that we want to talk about? Well, the behavior is whether it's tensile or compressive, right? Whether something's in tension or compression. And I think you have a pretty good intuition for that at this point, especially after taking statics, right? The classic thing is that cables, they only handle tension. Cables, strings, right? They're not going to be able to handle compression. They are going to become a spaghetti noodle that buckles or flops, okay? So if N1 or N2 are greater than 0, the bar will be in tension, and it will be stretching or straining that bar apart. Again, foreshadowing. We're going to spend a lot of time. One of one of the big things about this class, the extension of statics, is before you thought about internal forces, internal moments, torques, and you could do all this nice work with calculating what they were. But maybe at the end of the class, but definitely not in the middle, did you focus on, will the material break? Will the structure break? And how much is it actually deflecting? Okay? So in this class, what we do is we introduce principles that allow us to calculate how much extension, how much compression in terms of units of length, for example, you might be experiencing, or how much internal stress there is in a structure. Okay? Any comments, questions on this? Okay. So if I drew an arrow going inward to that either one of those open faces, then I would say what you see in this next slide. All right, we would say this one is going to be in compression, all right, and this one over here is going to be in tension. So this, if F is greater than 0, then it's in tension. If the F is less than 0, right, so it's been drawn this way, but this quantity, its magnitude is less than 0, then it's going to be in compression. Okay, and if F is greater than 0 over here, all right, then it will be in compression. If F is less than 0, then it will be in tension. It sounds very, very simple. We're starting very, very simple. But I've told you before, one of my desires when I have approached many problems in life is it up or down? Is it positive or negative? I just can't sometimes decide. And even though you have a 50-50 chance, you sit there and you look at the paper and you get paralyzed for 15 minutes. And you're like, I don't know. Is it compression? Is it tension? Okay. Now, what do we do when we have a bar that has multiple loads acting on it? Okay, so the way this is drawn, it may not be the most beautiful drawing, Okay? But there's a force A acting externally on the bar. There's a force B acting externally on the bar, force C acting externally on the bar, and force D acting externally on the bar. Okay? I don't know. Just imagine this is a game of tug of war, and this is a rope, and you've got some kid over here, and some kid over here, and some kid over here, and some kid over here. And which team, or who's going to win this tug of war? Well, if this is a statics class, no one's going to win, right? Everybody gets to win together, all right? But they're going nowhere, all right? Or they're going somewhere with a constant velocity. So that could be possible, all right? That is possible. This system is going round and round in Earth's orbit, okay? Anyway, we won't go. But you get the point. There's not really a winner here. Everyone is, let's be positive. Everybody's a winner, okay? So how do we approach this? Well, we approach, and what are we trying to figure out? We're trying to figure out what the internal loads are between, say, person A and B, and what are the internal loads between B and C, and what are the internal loads between C and D, right? So even though there may be a tug of war and no one's going anywhere, okay, the rope can be experiencing very different things between these individuals that are applying external forces to it, right? So this region can have a different force than this region, that can have a different force than this region, okay? But before we do that, it's probably advisable, okay? And I'll show you some things where sometimes you don't have to do this first step, okay? But sometimes you can just go right to method of slices if you're slick. Okay? But generally speaking, what we want to do is we want to first look at external equilibrium, and then we're going to apply Newton's second law. Okay? So to do that, we go ahead and we define our coordinate system to be plus x in this direction. And then what we do is we say, all right, there's a force going this direction, which is not the plus x direction. Then FB is in the plus x direction, FC is in the plus x direction, and FD is the plus x direction. Okay? Now, do we know how to solve for any one of these quantities if we have the other three? Yes. Okay, that is true. And in reality, that's all we could do. We need to know, with this one equation, right, we need to know three quantities in order to be able to solve for one. Right? And often when you have a system and you're an engineer, right, you kind of get another engineer or someone else to tell you, these are the system requirements. These are the forces that your system is going to be experiencing. So if you were given all the forces that the system is experiencing, then this should equal 0 if it's not accelerated. Okay. Now, what if we want to figure out what the internal force is between A and B? So what do? Well, we're going to take a slice. We're going to use our method of sections, method of slices. Again, we're going to define a coordinate system. Okay, so we draw it and we define a coordinate system, okay, which we can say is going to be like this, plus x. And we can then, at this point, just do the math, right? So you see this FAB. So often, or sometimes, we'll use that subscript to kind of indicate, a subscript with two letters, right, to indicate that that's an internal force. This FA is an external one. So now we have only these two forces here. And so if I know FA, then I know FAB, right? So this is where I didn't really need to do external equilibrium. If all I had to do was answer, hey, what's the internal force between A and B? You're like, I'm going to save 30 seconds. I'm not going to do external equilibrium on the whole system. I can go right to method of slices and know that FA is equal to FAB. Okay? Now, what about the second section? Well, this is a little bit more complicated, right? Because I have gone past the B, and I see that I've now got to draw another FBC. And you're like, wait, but I had an internal FAB. We don't care. We don't care about what's going on between A and B now, right? But we do care, right, about these external lobes, FA and FB. Right? So, how would you write out the math for this one? Yes?
We'll write the FB in terms of FA and FBC and then just replace the FA with FAB.
Okay, so if I want to know just an equation that says FBC is equal to
FA minus FB.
yes, right? Now we did that a little bit fast, right? But we could sum them all equal to 0, which is what we have here. Okay. All right. So FBC is acting in the positive x, as is FB minus FA. All right. And so that FBC is equal to FA minus FB. Okay. Any questions on this? Again, probably the math is not hard. All right. This is we're just creating some mental pictures. Now, how would you go about solving for F subscripts CD? Any suggestions? What would you do? We'll do someone else. You got it, you got it, you got it. What's your name?
Jack.
Jet, okay. Someone else. How, yes.
Did you start from the right side instead?
That is a very good shortcut, yes. So that is one way to do it, right? So if you start from the right side, what is FCD?
B equal to F.
That's right. That's it, okay? So I'll first show because I have it in a certain order, I'll first show that not that way, and then we'll talk about what you just said. Okay, what's your name?
Jake.
Jake. Okay, thanks, Jake. All right. So this is an extension of what we just did, right? Where we have now FA, FB, FC acting on the system. We have a coordinate system plus X. We have FCD. We can then write, okay, like minus FA plus FB plus FC plus FCD is equal to 0, which means that FCD is equal to FA minus FB minus FC. Okay, and we could also do what Jake just said and shortcut and just say take a slice, make FCD go the opposite direction, okay, and have FD. Notice this is where we say, look, are these FCDs acting in the same direction? No. But are they describing the same internal behavior?
Yes.
Yes. Okay? And this is maybe a little bit counterintuitive. Okay? And FCD is positive in both cases. That section will be in tension. Okay? So, FCD in this case is just equal to FD. But you're like, wait, I said it was equal to FA minus FB minus FC. Well, what do you use? Boom. You go back to the external equilibrium at the very beginning. And we can write and we can see that FD is in fact equal to FA minus FB minus FC. Okay? So there are multiple ways to attack this type of problem. Okay? And I think it's, we're going nice and easy for everyone. But once again, this idea that FCD is the same when it's going in opposite directions is going to be confusing, especially when we do our efforts with torques, which we're going to do in a second. Okay. All right. So in the homework, all right. Yes. Let me see. How am I doing on time? Let me if we have time, I'll go back and I'll like attack these going backward, but I think I'm going slow enough that I probably need to move on, all right? But we'll also have, I'll try to get some videos up on how to do these, but I think these are pretty straightforward based on the discussion that we've just had, okay? So here will be another one where we had to find out, again, FCD, all right, between these, and, in Canvas, there will be numbers instead of letters. And then there'll be a question about whether or not, it's in tension or compression, right? So pretty straightforward. So now let's talk about static equilibrium for torsional loading of a shaft. Okay? And in this case, the two rules still apply. We first perform external equilibrium, and then we do internal equilibrium. So we have to define a coordinate system, and we have to apply Newton's laws. So here's the coordinate system. I've arbitrarily picked it coming out positive on the A side of the system. Okay? I could have done it on the opposite. It doesn't really matter as long as we're consistent with the particular aspect of the problem we're trying to solve. And then we have the opportunity to apply Newton's second law. And for that, where is it? There it is, okay? So we have TA minus TB is equal to 0, and so TA is equal to TB. All right, so that's pretty straightforward. Yeah. Second step is take a slice, and this maybe gets a little bit less intuitive, but it's still pretty simple, okay? How would you draw the coordinate system in this drawing, and how would you draw the unknown internal torque? Yes.
Drawn in the same direction as TA.
Okay. So you're proposing that I draw it like this?
No, in the opposite direction, acting in the torque of the TV.
Okay, so I would draw it like that,
Acting in a rotation.
and I would draw it like, whoops, that,
The opposite.
in the opposite direction. I'm trying to help you out, man. You want to draw it like this?
Try it. Yes.
Okay. So it's a free world in the United States. So you could do that. Okay? And in reality, in this problem, that would not give you the wrong magnitude, right? Because we know you have an intuition, right? What is the magnitude of the internal torque? TA, right? That's the magnitude, right? It's just going to be the same, okay? What we're doing here, okay, is we are going to follow this convention where we usually say that the coordinate system that we want to use is again coming out of the face in the positive direction, okay? So I draw my coordinate system. In this case, we'll call it Z. And we say it's coming out of the cut, out of the slice, okay? And then I have to follow the right-hand rule, okay? And so I use the right-hand rule, and it's coming, well, let's see. Which way are you guys? Yeah, it's coming off like this, so I'm twisting like that, okay? So my TAB is going to look like that, okay? What's your name? I gave you a hard time. Otto?
Yeah.
All right, great, Otto. Thanks. Thank you for contributing. Yes. What are you saying?
I don't know if I'm asking it right or not, but does it depend like the direction of EAB that will have like the center of the like shaft thing. If it's like after the center of that thing, it's in the same direction. If it's before, it's in the opposite direction.
Yeah, so a couple things. So the first thing, I think you didn't say this, but I thought you might have said this. Does the direction I define TAB depend on the direction TA is? I thought that's what you were going to ask. And the answer is no. All right? We are trying to follow a convention. Okay? And so the convention is draw it out positive from the surface that's been cut. Okay? Now, think what you might have been getting to is if like this axis is here versus here versus here, does it depend on where it is? Maybe is that what you were saying on the cross section?
No. So like if the shaft is like a let's say 1 meter long shaft. Right?
Yes.
And if we are exactly taking a piece of the shaft at like 0.5 meters.
Yes.
Right. So up to that point, is it like the torque on the shaft like in the same direction as A part? Or
Yes.
Is
Okay, good. So, yes, and your name again is?
it J?
Jay. Okay, so what Jay is asking, I think now, maybe I'll get it right this time, is if I took the slice here versus here versus here, all right, is there a change in the internal torque? The answer is no. Okay? There is not a change in the internal torque until we get to another external load. Okay? So that's not always the case. You can have a distributed, if you have a distributed torque being applied to this system, which you will see examples on the exams of that, okay? Then yes, that internal torque will be growing or shrinking, okay, if it's like distributed. Imagine an elephant on a shaft twisting it, like or like a snake, and somehow that is able to apply distributed torque, or better said, a rope. Okay, so yeah, that's these are good points. All right, now we apply Newton's second law, and we see that TAB minus TA is equal to 0. Now you see, this is exactly what we did on the previous slides, but because it involves a shaft and because it involves torques, it just seems like it's a little more hard to grasp. All right. A little harder to grasp, but it's still pretty straightforward. Now, what if we slice the other direction? Well, same thing, all right? We have TAB, and I'll go through this kind of slowly. Again, we're going to come out positive. Again, we'll have a TAB. Again, we'll follow the convention. And again, we'll find that the internal is going to be equal to TA, because TA and TB are the same. Yes?
So, just so I follow, the convention to go through the face, if you chose the other convention going out of like just the end of the bar, you would just get a negative answer and no, you did it.
Right. Yes, that's correct. That's correct. And are you wrong in doing it that way? No, not necessarily. Could it lead to potential confusion down the road? For me, yes. Maybe not for you, but yes. And that's one of the reasons why we use conventions, is so that we can communicate what we've done in our calculations to other people. So if your classmate does it without the convention and you do it with the convention, you're going to have a disagreement in your answer, right? Okay, so good points, everybody. Now, before, remember we just said we had compression and tension in a bar. But what's the behavior that we have in a shaft? Is there tension? Is there compression? Well, I think you already have an intuition for this that no, it's not the same. Okay, somehow it's not the same. It's just a matter of which direction is stuff twisting. Okay, and this insight is also, I think, helpful. All right, okay, so this is kind of whatever, we understand this, right? That if TA is positive, because this is what the algebra tells us, okay? But what I want to point out here is before you do a lot of these problems, it's just very good to take a step back and say, what would this look like in the real world? Okay? Like, if I take my pen and I twist it, right, like this, and I gotta draw these moments on this bar, on the shaft, right? What would it look like? Well, I have an intuition, right, that this system, if I twist, right, if I apply a moment, how do I do this? Oh, no, I can't do it, all right? Actually, maybe I should do it like this. Yeah, there we go, right? So then now I'm following my convention, right? This is right hand, this is, right? So you've got an idea that a piece on the top here is going this direction, and a piece on the top here is going this direction, right? We can kind of imagine that deformation, okay? And so what we're going to do later in the class is characterize the stress and the strain on these three different types of objects. And with torsion in particular, because it's not, I know if I'm, it's pretty intuitive, okay, you put me in a press and I'm being compressed, okay, right? And like I get shorter. But here it's a little bit less intuitive. So what is often helpful is to draw a grid on the object. And when you draw that grid, you can pick, let's say, one of those elements, okay, like that. And so this is, imagine this is a grid, again, this is my very poor drawing, okay? My 7-year-old can draw better than I can, okay? There's a lot to be said for growing up with a lot of paper that you can just scribble on. My kids, they can draw better than I can because I was scared of wasting paper, I think, growing up. Okay, let's not go into my Freudian issues. But my kids, they have, we're fortunate where there's a lot of paper and wasted paper that we just throw out in a cart for them, and they just scribble on it, right? And it's already been, you get enough junk mail in the United States that you can just well, we don't usually give them junk mail, but they don't have clean sheets of paper. Anyway, what we do here is we think about what is happening to this grid when it's been deformed. So if I apply the torques like you see here, right, you can already see that this side, let's say this side corresponds to this side, and this side corresponds to this side. Do you see that? Well, what's going to happen? This side is going to shift up, and this side is going to shift down. Okay? You see that, right? Pretty simple. And then I draw this element, and that's exactly what I draw. Okay? I say, oh, the left side went up, the right side went down. Okay? This is what. Then I assign these arrows to it, and we have our introduction of what shear looks like. So we'll talk a lot more about shear. Many times we'll be talking about shear stresses, we'll be talking about shear strains. But this is a way to kind of visualize these arrows as being somehow forces, but they're not really forces. We'll call them stresses later that cause the distortion of an element. And there will be associated shear strain with this, and that ends up having units of angles. It's actually an angle that we think of when we talk about shear strain. But that all comes later. What the point is, we can think of the behavior here in terms of a direction in which we're having our deformation. Any questions on this? Okay. Anyone done any numerical simulations, using different finite element packages or anything? Yes, right? So does this look kind of like that, right? Lots of you draw little elements on it, right? And you see what happens to these elements. That's at the heart of what we do in a lot of our numerical simulations as mechanical engineers. We discretize the entire system, and then we look at how all those discrete elements get deformed. Yes?
So I'm also going to guess that this makes a nice connection to linear algebra, just because
Yes. So we will do a little linear algebra at the end for trusses, but yes, what you end up having, all right, when you have all these elements and they're all acting together is a set of matrices. Okay, you have a forcing matrix, you have a stiffness matrix, and you have a deformation matrix. Yes?
For the length, for lines that go across, do we still have to keep their total length in mind when we're drawing the shape?
Okay, so So I'm not sure I understand. Here, just like we were saying before, it doesn't depend, right? The actual magnitude of the internal torque doesn't depend on it, but the amount of twist, the angle of twist, which we will talk about later, very much depends on its length. Very much does. Okay? So this is another thing that we talk about. Great. Good stuff. All right, so if we have multiple loads on a shaft, okay, once again, we first do external equilibrium, then we do the slicing, and we are going to define coordinates, and we're going to be careful here. So you already got the idea, right? That if I am looking at what TAB is in this system, do I really have to do external equilibrium first? No, right? Because I can just use the slice, I can use this information, what TA is, right? And similarly, if I have a system where I'm interested in what this TBC is, okay, I could do the shortcut and just say, oh, it's going to be related to TC. Or I can look at adding up things, all right, like we have here, and then saying, okay, that's what TBC is equal to. And, or I look at it this way, all right, and it's going to give me an idea of what it is and how it's equal to TC. Okay. I did that kind of quickly because I'm going slowly, but do you have pretty intuitive questions, thoughts? Yes.
So when you're cutting, when you're doing like the section method, when are the torques are not going to be equal to each other?
Good question. Okay. Well, equilibrium has to hold. Okay? Equilibrium has to hold. So if I had another external load acting along this, then it wouldn't just be equal to either the left or the left side or the right side, right? But you already can see that TA and TC, as long as TB is non-zero, they're not going to be the same. So at least at this point, we have TA and TC not being the same. Okay? Good question, though. But this is completely analogous, right? We did FA, FB, FC, FD just a second ago, right? Where we had 4 forces in the tug of war, right? This is like the twist of war, but we've only drawn 3 here. Okay. Good. So in the homework, you get a chance, and I'm sorry they're going to be out of order. So notice Q6. There are 6 questions. I just messed it up when I made the order. So Q6 is the last one, but it's actually a torsion problem. Okay, transverse loading on a beam. Oh, and I left some of my old notes here, so sorry about that. What do you do? First, external equilibrium. Define the coordinate system, and then apply Newton's laws. Okay. Second, we're going to take a slice. Okay. And then we'll use the method of sections, and we will be able to apply Newton's second law. Now, let's go through this a little more slowly, right? So the procedure is exactly the same. There are some details that we need to cover. So first, when you're doing external equilibrium, you don't have to worry about conventions. I probably should have said this earlier, but I didn't, just because I forgot. It actually did go through my mind, but I forgot to say it, or I got distracted. What do I mean by that? You see this wall is acting as something that provides external constraints. A firm wall provides 2 constraints. It provides a constraint on force, and it provides a constraint on moment. And sometimes a wall will also have an axial force. Okay, so like if I had put an axial force coming out of here, like what I'm saying is if there were an axial force here, then I could say, oh, the wall also is providing an axial force. But that's not the main focus right now. So there's not a convention that I have to follow when I'm dealing with external loads. I can draw MR the opposite direction if I want. I can draw FR the opposite direction if I want. But why did I draw them the way I drew them? Any ideas? Yes.
So that like the sum of forces is still zero in rotation.
Okay, yeah, so that's always going to be true. Okay, all right. Anyway, yeah, okay, Michael, all right. Why else might I have drawn them the way I drew them? And specifically the directions I drew. Yes, Brent.
Counterclockwise by convention is positive.
Okay, yeah, so again, though, I don't have to follow convention, but that would be a good, like, feeling, yes, yes.
Just so that it can be equal opposite to P in the moment.
Yeah, so I'll say it another way. I wanted positive numbers. That's all, right? Look, FR is going to be equal and opposite to P, like you just said. What's your name? Raymond. Okay, Raymond said this, right? So that means that FR equals P. If P is positive, FR is positive. If I had drawn it the other way, then I would have gotten a minus P. All right? Similarly, MR, right, the way I've drawn it, it's going to be equal to PL. So when you're picking your, unless you want to be a negative person, which I often am, all right, but typically you want to have just the positive, you want to pick quantities that will give you positive results. Okay? Just to make it one less negative sign to carry in your algebraic calculations. But again, you don't have to do that. Now, internally, yes?
Would there be any questions or like situations where we would be like bound to take it in the opposite direction and get a negative answer just like for the sake of that question?
I think if someone gives you, if I give you numbers that are like negative quantities and you see a vector and the, you gotta just be careful. Hopefully I won't be that mean though, okay? Usually I use positive numbers for the external loads and I draw the arrows appropriately for that, okay? But yes. But this, you're foreshadowing, you're leading into the next thing. You do have to follow the convention when you do internals, okay? You must follow convention if you want correctness, okay? Because we have to be able to communicate with each other, okay? If you tell me the internal shear force is negative, but I say it's positive, I'm right, okay? So we have to be able to communicate that. So the conventions that we use are in Hibbler's book, all right? So if you slice and you have the open side exposed, then down is the shear force and counterclockwise is the internal moment. These are not negotiable for this class. When I started teaching this class, or actually when I started teaching DMC, I was like, why? This is so weird. These conventions are so weird. I don't, I was like, this is not, or when I started, maybe it was when I started teaching this class, it's like, why do these conventions? And then I look back at my textbook when I took the equivalent course, that book uses a different convention. I was like, so now I have to unlearn what I learned. Okay, so I will often write these down, and on your formula sheet or on your note sheet for the exam, you probably just want to write this down somewhere, okay, so that you remember what the convention is, or are, conventions are, okay? If you're exposing the right side, then V is down. If it's exposing the left side, V is up, all right? And I didn't even say, right, but I think you all know. V is the shear force, internal shear force, right? And M is the internal moment. Notice once again, though, the V's describe the same behavior. Like I can take a bar and slice it and leave the right open, right? And when so let me look at it. I slice it and I leave the right open, right? And when I do that, I have a positive V going down. Or I can slice it and leave the left open, right? And then I have a positive V going up. Or right there, right? Wherever the slice was. And that's bad. I'm not a good mind. All right, so these V's, even though they're in opposite directions, they describe the same behavior, and they're going to have the same magnitudes. This is an intricate, difficult point to grasp, I think. Because it's like they're in the opposite directions. But no, they are the same, just like the moments are. The moments are in the opposite directions, but again, they describe the same internal behavior. All right, so once again, with the moments, we had to make sure that we pick a location, all right? And, if we pick the location as being at the left side, that's often convenient, okay? And so here, right, this is a little bit trickier, and I'm going fast, but you did this in statics a gazillion times, all right? So I have an M, and I have now a moment from the V, and that is going to be twisting it in a negative direction, right? Do you see that? It's going, and it's going into the board, right, at this Z point. Okay, Z, the dot in it, that means it's coming out of the board. Okay, but the moment that's being applied by the V is going to be minus the length to this location. So X really is going all the way out to there now. That's the X. Okay. Any questions on that? Yes. Yes. It's always counterclockwise when you expose the right side. It's always clockwise when you expose the left side. Okay? Yeah. In this case, when I've exposed the right side, it's always counterclockwise. So just write this little thing down on your sheet of notes, and you'll not get confused. Any other questions? Yes.
So for that third example, does that mean you're just going to have a negative reactionary moment?
Okay, so it depends, right? It depends on what the XV is, right? Yeah. But we'll talk about that in a sec, all right? In graphical form, because you also are experiencing graphing these. What did you have a question?
And also, would X be like a variable, like the length of the?
That's right. So this is a case where, remember we were doing these nice examples with torsion and with bars, torsional loading and axial loading with bars, right? Where it was a constant. The force didn't vary from one, interesting point to another. This is an example where the internal moment is going to depend on where the slice is along the beam. Okay. So this is the equation. So here we go. Essentially now answering, I don't know, what was your name? Parker, right? What he was saying, is this going to mean it's negative? Well, MR is not negative, right? MR is positive, okay? But the internal moment is, as you say, going to be negative, okay, like this. See that? Okay. Now, why did you spend a whole semester making these plots? It's so you could come to this class. No, but yes. All right? It's so that we could calculate internal stresses and calculate deflections. So it's not going to be a long time before we get to answering this question, right? Where we say, oh, sigma, the stress, the axial stress is going to be proportional to the internal bending moment. Okay? And there'll be some factors and things and locations and properties and whatever. But the exercises you did in the previous semester are to get us to this point where we can figure out whether or not things are going to break and how much they're going to bend. And then if you like, there's some Python that you can use to be able to do things graphically. Okay? And then we'll do some example problems. All right? And it's probably a good idea, actually it's a very good idea to review what it means to have distributed loads on a beam. Okay, so do you remember this? All right, that's the easy one. That stresses me out, right? Okay, maybe it doesn't stress you out, right? But right, you got to figure out where the effective force is acting, and where is the effective force acting on this one? Yes.
Centroid. Or the 1/3 the.
So it is the centroid. You are right. It's the centroid, and it's 2/3 away from the zero end, right? Or 1/3 away from the big end. Okay, and the effective force is going to be 1/2, right? It's a triangle, so it's 1/2 times W max times the length of that load. Okay, so that stuff you want to probably review that too. Okay, all right. Trusses. I've got 10 minutes. Do you have time? Do you want to get your attendance, sir? Do you want your attendance?
Oh, I'm sorry. I just got to run out of work and I had to leave.
Oh, okay. I'm sorry. Well, I was just going to offer, if you can stay for 1 second, then you can get your attendance.
Oh, I mean, I just had to run.
Okay. Well, either way. So let's do this. All right. So anyone, let's go ahead and do attendance, and then I'll take this thing home. All right. All right. So go ahead.
Could I take an attendance earlier?
No, because you need this yellow thing.
I can resubmit it.
Yeah, you couldn't take your attendance earlier. You needed this. Oh, that's okay, but I can see we can see the yellow. Yeah. Huh? All right. Okay, everyone. Okay, we're still, yeah. Yeah, it's fine. Resubmit it. Yeah, of course. Did they shut down?
Yeah, we can't do multiple tests.
Ah! Okay, take a screenshot. Or take a shot. Take a picture. Just take a picture. All right. And then if it's an issue, we can work it, or you can add a comment or something. Like, you can definitely go in and you should be able to submit a comment on it. Yes.
You can add it as a comment.
Yeah, you can add it as a comment, right?
Yeah, you can just add it as a comment.
Yeah.
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 You open, you click submission and click, and then process.
Okay. Have a good one.
Sorry, I also had to go to work.
Yeah, okay. I understand. Okay. All right. So, are we all set? Everyone got a picture at least, right? Okay. So, let's cover the last topic. Okay. So, trusses. Does everyone like trusses? No. Okay. That's okay. We're honest, right? Okay. Guess what? The methodology is surprisingly similar. Or is it maybe not surprising? What do? We first do external equilibrium, and then we do internal equilibrium. If we're using method of sections, or if we're using method of joints, we also do a form of internal equilibrium, right? So this looks familiar. With the method of joints, does anyone remember the advantage of the method of joints? Is there an advantage to method of joints? Okay. So the method of joints allows us to calculate the forces in every member of the truss. Okay, do you remember that? Okay. Whereas method of sections can be faster, all right, and it allows us to calculate out. All right, so this is the method of joints very quickly. What do? You say there's a joint, and then you draw vectors. So let's say this is joint A right here, and we have the forces from the wall here, reaction forces, A, Y, and AX, and we have forces from the members. If it's coming out of the node and it's going into a member, is that member going to be in tension or in compression? Do you remember that? If it's coming out of the node or out of the joint, yes? Tension, right? And if I draw it going into the node, then I'm saying that means that those members are in compression, right? Because they're like, you can kind of think of it. These joint 1, joint 2, right? Those are forces that are acting outward on the nodes. Okay. So you can use algebra or you can use linear algebra. Okay, like you see here, right? There was a question, I think someone said something about linear algebra, right? So we can use linear algebra to solve these. In the future, okay, not for this assignment, you'll have an opportunity to use Python to be able to do these calculations, right? And I'll show you how to do that, and it'll be nice and happy and fast. Okay. Method of sections is nice because you take a slice and you can quickly evaluate what the internal forces might be in certain members without. So you see this, you're not going to be able to figure out what's in this member, but you can figure out what's in those members. Okay? And it's usually less math to figure this out. Okay? Method of sections can be useful when we want values in a few members instead of solving for all members, which is what the method of joints is. All right, so the takeaways for today. We love static equilibrium in this class. We will use it for external equilibrium first. We will use the method of sections or the method of joints if it's a truss. And we will be able to solve for the internal forces and moments in our structures. Thank you very much. See you on Tuesday. And remember, we have the safety training on Tuesday, so please be here. It will save you time.